Okay, today we're going to talk about antennas and feed lines, and then the second half will be propagation. So it's a good thing Byron's here because he knows all that stuff. So he'll keep me straight.
Should I bring my power meter and SWR bridge in?
No, probably not necessary. And the first are antennas and feed lines. There's 4 groups, so that means there will be 4 questions out of this. So you'll get one on feed lines and SWR stuff, matching. You'll get one on dipoles, and one on directional antennas, and one on specialized antennas. Byron may show us one of his specialized antennas in the box back there, a new screwdriver, and there's a chart on that. So the first thing we talk about is characteristic impedance of feed lines, either twin lead or coaxial cable. And it's defined as the impedance you see on a transmission line of infinite length. And not many people have an infinitely long transmission line. So if it's a finite length, if you terminate it in its characteristic impedance on each end, it appears to be it's infinitely long, and you get no reflection from the load, your antenna or whatever you're connecting it to. In our world, it's usually an antenna. The formula for the characteristic impedance, which you don't need to know, is just the square root of the inductance divided by the capacitance. And it's a distributed inductance capacitance along the line. And if you do a little calculus and integrate them, that's what you wind up with if it's infinitely long. The key thing is you need to terminate it on both ends in its characteristic impedance. If it's not, then you're going to get a reflection, and that will give you an SDR of something other than 1-to-1. And we'll talk about that a little more. If you have a parallel conductor transmission line, such as twin lead, window line, ladder line, the characteristic impedance is determined by the distance between the conductors and the radius of the conductors. So the farther apart they are, the higher the impedance. Ladder line is about 6 inches apart. Standard TV twin lead, which is probably a ½ inch, is 300 ohms. And the one in the middle, which we call window line, is 450 ohms. That one's on the test. Coax is similar, but its characteristic impedance is the diameter of the center conductor and the inside diameter of the shield. So you've got the distance between them basically embedded in that equation. And if you notice, I didn't talk about this one, but the only difference is a factor of 2 in this formula on whether it's coax or twin lead. We typically use 50 ohm characteristic impedance coax, sometimes 75 ohm. It could be a better match to an antenna like a dipole, and maybe a little less lossy. Typically, 75 is used for TV broadcast and reception. So which of the following factors determine the characteristic impedance of a parallel conductor feed line? Alpha, distance between the centers and the radius of the conductors. Okay. Did you ask why it's usually 50 ohms? If you did, the answer is it's a compromise. And they determined, and this was basically AT&T back in the early days, that 30 ohms was the best for power transmission. The broadcast industry went with 75 ohms because it was lower loss. So when they decided to come up with this sort of standard, they took the mean and the median of the two and averaged them. And that came out to like 49.9 something ohms, which is why we use 50 ohms. The antennas can vary anywhere from just 10 or 20 ohms up to thousands, depending on the feed point and configuration of the antenna. Whenever you have a mismatch of impedance, in other words, your antenna is a different impedance than the feed line, you're going to get a reflection, and the little wiggly at the bottom is showing, in this case, it would be 100% reflection. But if you, and it doesn't matter which one, if you assume the blue line is the wave that you're transmitting, you'll see when it gets to the end here that it gets reflected back 180 degrees out of phase. And as that comes back, it tends to add and subtract. So in this case, you're going to get a standing wave that's double what you're actually transmitting. And of course, there's nothing getting to the antenna in that case. And you're going to heat up the coax.
And final output of the transmitter.
Yeah, you won't do it any favors. When you get above 1.5, the new ones will usually start throttling back. You can determine the ratio, the SWR, by the ratio of the impedances. So if I was feeding a 75 ohm antenna with 50 ohm coax and a 50 ohm transmitter, I'm going to get a 1.5 SWR. If I was going to 35 ohms, which is one of the impedances you can see on a dipole when you lower it close to the ground, you're going to get a 1.3 to 1 in that case without any sort of matching. And you can operate in those ranges. Most of the newer radios have built-in tuners and will handle that easily. And even without a tuner, you can still operate. So how do you get around it? You use a matching network. And there's basically three things. You can put an LC network in, and most of these things that are sold as antenna tuners or the ones that are embedded in the radio is just an LC network. And either you manually adjust the inductance and capacitance to get a conjugate match. In other words, you want to get the opposite amount of reactance that you're seeing on the other end of the antenna. So if your antenna was looking inductive, it's going to have a plus reactance. You'd want to crank in a capacity reactance equal to that, zero it out. Another thing they use is a quarter wave transmission line transform. In other words, you take a piece of transmission line, shorten one end of it, and have it a quarter wave long for the frequency you want to match, connect that to the antenna, and that will act as an impedance transform. Then there's also Balun and Unun transformers, which you'll see on end-fed wire antennas, on off-center fed. You got one on that? Yeah.
40,
You could use one for a horizontal dipole that was 75 ohms. And you have to play a little bit to get the right turns ratio to
And 5 to 1 on this.
yeah. And like Byron said, for like in-fed wire antennas, typically you use a 49-to-1 transformer, sometimes 64, and even the next one up. What?
The 49-to-1 to 64-to-1 are for the in-fed half waves, 9-to-1 grain required.
Okay. The main purpose is to try to prevent the standing waves, so reduce your SWR. And prevent the reflected power coming back, because that is power that's not getting to the antenna. It turns out that a little bit of it may, because as it's reflected back, some of it's lost in the transmission line coming back, just like some of it was lost going out. And when it gets back to the transmitter, it can be reflected back from there. So you get a little more loss, and a little more of it gets to the antenna. So it's not totally lost, unless you have very lossy feed line. What causes reflected power at an antenna's feed point?
Yep.
Okay. When you're not matched with the same impedance. What must be done to prevent standing waves on a feed line connected to an antenna? Yep. You need to match it as close as you can. Standing wave ratio. It's a measure of the impedance matching of the load to the characteristic impedance of the transmission line. This sort of assumes that your transmission line and transmitter are both the same impedance, which usually are. If the transmission line is lossy and you have a high SWR, you're going to get additional loss in the cable, because you're actually going to have a lot more current due to that standing wave than you would without a reflection. So there will be more heating of the coax and more loss in the coax or the twin lead. Because of that, if you have an SWR meter at the transmitter end, it can read actually lower than what the SWR really is, because of the loss of the reflected wave coming back. So you don't see as big a reflection. And the formula down here, the way the digital SWR meters work, is they take this ratio of the reflected to the forward power in that formula, and that's how they determine the SWR, based on measuring forward and reflected power. Let's see. I'm not sure what I intended with that one. Couple examples. If the load resistance was 200 ohms and you got a 50 ohm transmission line, your SWR is going to just be that ratio of 4-to-1. If you had a very low impedance load with 50 ohms, you still take the higher number in the ratio, because it's always going to be a ratio of greater than 1, either 4-to-1 or 5-to-1, depending on whether the resistance is higher or lower. So what is the effect of transmission line loss on SWR measured at the input to the line? at the transmitter end. Right. What is the relationship between high standing wave ratio, SWR, and transmission line loss? Well, let's see.
And the question of myself, well, you know,
Huh?
you had the question of myself, I'm going to read the others. So
Yeah, you always need to read them. And sometimes they word them and they're a little tricky.
it's a trick question.
No, well, you know. What standing wave ratio results from connecting a 50 ohm feed line to a 200 ohm resistive load? Now they throw in resistive load, so you don't have to worry about any reactances and complicates the equation.
More and more.
Okay. You always want the bigger number on top when you divide. What standing wave ratio results from connecting a 50 ohm feed line to a 10 ohm resistive load?
Doggy. All right, we're not using phonetics, guys.
What is one reason to use an impedance matching transformer at a transmitter output?
Um,
If the SWR on an antenna feed line is 5:1 and a matching network at the transmitter end of the feed line is adjusted to present a 1:1 SWR to the transmitter, what is the resulting SWR on the feed line? You can call that a trick question, but it's a fundamental question. All right. It doesn't matter what you do on the transmitter end.
Still got the SWR.
If it's a mismatch with the antenna, it's a mismatch at the antenna. That's why in some cases you put a matching network at the antenna and the feed line. And there's even remote antenna tuners that will automatically adjust, like the one in your radio. So you don't get the losses coming back on the feed line. Transmission line loss. Okay, there's the formula again for calculating SWR when you know the forward and reflected power. If the transmission line is lossy and you have a high SWR, it's going to increase the loss because with a standing wave, you got more reactive current through there than you would if it was a perfect match. And we know that I times R is so you're going to dissipate more of the reflected power, so you see less coming back. That's why your SWR meter is going to read low. Here I worked out using their formula what you would get with those kind of forward and reflected powers. You can see if I had 10 watts coming back and sending out 100, I've got an SWR of almost 2 to 1, which is about the operating limit that you'd want to do without some sort of matching. If you had a very lossy network, you're going to see an SWR 1.57, where you got another 5 watts that you lost in that reflected power coming back in this case. So you'd think you had a decent SWR, and it's really close to 2.
I think you're doing well, but nothing's going to happen now.
Well, some, but not all of it. And since the best you can do is get half of it, if you got a perfect match, you want every watt you can get, depending on the path loss. If you're trying to do something like moon bounce, you want every fraction of a dB. What is the interaction between high standing wave ratio, SWR, and transmission line loss? Yep. SWR increases the loss. What is the effect of transmission line loss on SWR measured at the input to the line? Alpha. Yeah, I think they really want you to know this because these are not the same questions, but they're basically asking the same question, several different ways. Antenna feed lines. Even a properly terminated line is going to have loss. We don't have any of those theoretically perfect ones. So the chart is showing you some typical coaxes where RG174 is the very small, like 1/8 of an inch in diameter. You use short lengths of it, like maybe going to test equipment, stuff like that, or where you really, well, one example is if you've got an antenna on your car and you have to feed it through the trunk or the door, whatever. Normally, they can have a section of RG174. It's very skinny, so you can feed it through that gasket and then go back to RGX, 8X, or 58 or something like that. RG58 was probably the most common of the 1/4 inch lines until they came out with 8X, which is basically the same size. It's a lot more flexible. It's about the same price. A little less loss in it than 58. And the main thing you see in this chart, regardless of which of these coaxes, as you go up in frequency, the attenuation goes up. So there's more loss per 100 foot, the higher the frequency. And we've standardized the loss or attenuation in dBs per 100 foot. They reference RG213 a lot. I've got a piece of it. I don't know. Do you use RG13? 213? I'm not sure why. It's about the same as RG8, characteristic-wise. 400 LMR 400? Yeah, that's the good stuff. Unless you can afford 600. Airport's not LMR 400 PV. In fact, I was reading an email this morning. There was a question He was on some of the QRP stuff on what was the best coax to use for a QRP rig. And a guy said, LMR 600 and a vise to hold it
Yeah.
because it is stiff. The key, though, is loss increases with frequency. And as you go up in the size of the coaxes, if you go across from left to right, they have less loss because they're larger diameter, so the separation is more, and they have better insulation dialect. Window line, which is not in this, it doesn't have any of the twin leads, is much lower loss than most of these. And the ladder line is lower loss than window line. But it's not as convenient to use. In fact, I guess I've never run it. Do you have to avoid it getting close to metal and stuff?
You know, we're supposed to, well, in the American on the outside. I know that some people run it up the tower and they use like a 6-inch handle. It's like from their tower.
That's the nice thing about coax. Nothing is supposed to affect it in theory. How does the attenuation of coaxial cable change with increasing frequency?
Yeah. Really. Or the phonetic. He has it not.
Okay. The attenuation increases. In what units is RF feed line loss usually expressed?
Oh, I'm not gonna be right.
Yeah. Well, there's usually only one that's right. You didn't read carefully. You almost made a mistake, didn't you?
Yeah.
Decibels per 100 feet. We use ohms per 1,000 feet for wire resistance. I guess in some cases they may do 1,000 feet in dB for some really long wire stuff, perhaps. Normally, if you see your specification sheet for the cable, it's going to be in dB per 100 feet. Feed lines. Sometimes it's better to use a parallel transmission line feeding some antennas. And they're talking in this example, they say a non-resonant doublet antenna. Byron, tell me what that is.
One of the most popular would be the Carolina window. And it's just often on the dipole where you're getting about 1/3 one end. And, there's a couple of recipes on the length variance. And then at the feed point, you use a 1-1 transform. And you can run coax this way. I've used those, they are very good antennas. But I'm not the Impedance because, you know, they're nearly as good as a Westnet. All in your life, nature. Yeah.
And they do all the harmonics.
Yeah.
So if you got an 80-meter in-fed, you can get 40, 30, 20, 17, 15, or you get 17?
Yeah.
15, 12, 10, the whole shebang with pretty good SWR.
Yeah. Yeah, I don't even truly like the pathway that I can place. Or I do choke. Yeah, I do well, you know, choke at the that one and change it for you and then dry out.
Okay. There are several types of parallel transmission line we talked about before. the TV twin lead, which I don't think is used in amateur radio, except perhaps making a twin lead J-pole. A ladder line, which they call window line in some cases. It's usually 450 ohms. And then the open wire feed line, which is also kind of called ladder line, is 600 ohms. That's the one that's about 6 inches apart. And you can make your own. Some of the places like Tractor Supply that sell electric fence insulators, there's one type that's about 6 inches long, plastic, and you can use those as separators and make your own with just regular THHN stranded wire. Here's what they look like. This is over here, this ladder line is commercial with their little dog bone things. But there's nothing magic about it. It's just the size of the wire and how far apart it is. And the fact that that's a good insulator.
Also, sometimes if you just allow a little bit of a twist in your parallel line, that makes it a little bit quieter.
What is the nominal characteristic impedance of window line transmission line? 450. Yeah. Okay.